Welcome to Chapter 21 on Computer Vision. Here we explore how machine learning gives computers the ability to process, analyze, and make sense of images and video. Hold your phone up to a foreign menu and watch the translation appear over the printed words in real time. Computer vision is the branch of machine learning behind this, and we will build the subject up from the ground. By the end of this chapter, you should be able to explain what computer vision is and where it is used, describe how grayscale and color images become numerical arrays, define pixels, resolution, and channels, and apply basic preprocessing and augmentation. You should also be able to explain why convolutional neural networks suit images so well, describe filters, feature maps, and pooling, and understand transfer learning and when to reach for it. This figure shows a single convolution step. A small kernel slides over the input, and at each position, it computes a dot product with the patch it covers, producing one value in the output feature map. So what is computer vision? It is the study of how computers can interpret visual information. The tasks span deciding what an image shows, finding where objects are, labeling every pixel, recognizing faces, and much more. The most important idea in this chapter is also the simplest. To a computer, an image is just a numerical array. A grayscale image is a two-dimensional matrix, while a color image stacks red, green, and blue intensities at every pixel. A pixel is the smallest unit of an image, a single cell in the grid carrying a brightness or color value. Raw images almost never arrive ready to train on, so we pre-process them into a consistent form, resizing to common dimensions, normalizing pixel values, converting color formats, cropping to the region of interest, and reducing noise. One more pre-processing step is augmenting the data with realistic variations, which we will return to later in the chapter. Image classification is the simplest task. It assigns a single label to a whole image. Object detection asks a harder question than classification, not just what is in the image, but where it is located. Segmentation goes finer still, labeling every individual pixel in the image. Why not simply flatten an image into one long vector and feed it to an ordinary network? Instead, a convolutional network learns small filters that scan across the image hunting for visual patterns and stacks them into a hierarchy. A convolutional filter is a small grid of weights, often 3 by 3, that slides across the image. The crucial point is that these weights are learned from data, not hand-designed by us. Pooling shrinks feature maps to keep the network efficient, and it makes the network more forgiving of small shifts in the image. This figure illustrates max pooling with a 2 by 2 window. The feature map is split into non-overlapping blocks, and each block keeps only its largest value, so the strongest response in each neighborhood survives. Stacking these pieces gives the full classification pipeline. Convolution and pooling blocks alternate. The spatial size shrinks, while the number of feature maps, the depth, grows. This figure shows a complete classification pipeline. As convolution and pooling blocks shrink the spatial size, the feature map depth grows, building a hierarchy from edges to textures to objects before a final flatten and classifier. Training a powerful vision model from scratch needs millions of labeled images and heavy compute, which most projects lack. This works because early layer features like edges, textures, and shapes are nearly universal across images. Here is the key point. For almost any real-world vision project with limited data, do not train from scratch. Start from a pre-trained network and fine-tune it. Transfer learning routinely turns a few thousand images into a high-accuracy model. Vision transformers bring the attention mechanism that transformed language modeling back in chapters 17 and 18 over to the world of images. Different vision tasks call for different yardsticks. For classification, the metrics are the familiar ones from chapter 4: accuracy, precision, recall, F1 score, and the confusion matrix to see which classes get confused. Intersection over union, or IOU, measures how much a predicted region overlaps the true one, the area of overlap divided by the area of union. It runs from 0 for no overlap to 1 for a perfect match, with detections often counted correct above a threshold like 0.5. The IOU formula is one line, but watching it decide whether a detection counts makes it stick. We write each box by its corners, the bottom left and the top right. Two boxes overlap wherever they share both an X range and a Y range. The union is the area covered by either box, and the ratio of overlap to union gives us the score. This figure works through an example. Prediction A and the ground truth each have area 12 and overlap in a 3 by 3 square of area 9, so the union is 15 and IOU is 9 over 15 or 0.6, clearing the usual threshold. Now we score a sloppier prediction, a box of the same shape but shifted further up and to the right, and watch its IOU fall. Data augmentation expands a training set by generating modified copies of the images you already have, and it is one of the most reliable defenses against overfitting. The one rule: the variation must be realistic for your data. Computer vision now reaches into healthcare, manufacturing, retail, agriculture, transportation, security, and the environment. But models can fail badly when conditions shift. A new camera, unfamiliar lighting, an unusual angle, a cluttered background. Let us warm up with a small, no-download dataset so we can see the idea of images as numbers concretely. This code loads the handwritten digits dataset, displays the first few digit images, and then prints one image as a grid of integers so we can see the raw pixel values behind the picture. Printing that first image as integers drives the central point home. What we see as a handwritten digit, the computer sees only as an 8 by 8 grid of brightness values. Before reaching for deep learning, it is worth seeing that an ordinary classifier can already do a respectable job when image pixels are treated as plain features. This code splits the digit data, scales the pixel features, and trains a logistic regression classifier inside a pipeline, then reports its accuracy and a full classification report on the held-out test set. Logistic regression treats each of the 64 pixels as an independent feature, and it still scores well above 95% on these clean, centered digits. Now we build a real convolutional network in Keras for the fashion MNIST dataset. The code normalizes the images, adds a channel dimension, and stacks convolution, pooling, and dense layers into a classifier. Reading the architecture top to bottom, we can see the chapter's ideas in code. 2 convolution plus pooling blocks that learn and then summarize visual features before a dense classifier makes the final decision. Finally, augmentation through Keras preprocessing layers, the modern replacement for the older image data generator approach. This code builds a small augmentation block with random rotation, zoom, and translation. Dropped in at the top of the model, it varies each image on the fly while deliberately skipping horizontal flips that would be unrealistic for some garments. Each epoch, these layers nudge every training image a little, so the network sees a slightly different dataset every time and learns the clothing itself rather than its exact pixel arrangement. Consider a regional hospital whose radiology department reads thousands of chest x-rays a week. They want a vision model not to diagnose, but to triage, flagging the scans most likely to show a serious abnormality, so a radiologist looks at those first. This is image classification with unusually high stakes, and the design reflects that. Rather than training from scratch on a limited medical set, they fine-tune a model pre-trained on a large general image collection, the transfer learning move from earlier. The following code uses Fashion MNIST as a stand-in for the triage scenario, restricting it to 2 classes to simulate a binary normal versus abnormal classifier. This code filters Fashion MNIST down to 2 clothing classes, normalizes the images, and builds a compact binary convolutional network as a proxy for a normal versus abnormal triage model. The top confidence predictions represent the scans the system would surface first for review, showing how a simple convolutional pipeline can prioritize a radiologist's queue without ever replacing the radiologist. To summarize, computer vision rests on a single fact that an image is a numerical array, grayscale as a matrix, and color as stacked channels. Convolutional networks dominate because they respect spatial structure, building from edges to objects across layers. For further reading, look to introductory computer vision textbooks, the TensorFlow and Keras tutorials on convolutional networks and transfer learning, the PyTorch image classification tutorials, the OpenCV documentation, and applied case studies in medical and industrial imaging. Two landmark papers are worth knowing: LeCun and colleagues on gradient-based learning for document recognition, and Krzyzewski and colleagues who demonstrated the power of deep convolutional networks on large-scale image classification. That brings us to the end of Chapter 21 on computer vision, where images became arrays and convolutional networks learned to see.